Welcome to This Explainer. Today, we're diving deep into the macro and micro of complex hydraulic steering systems. Because let's face it, if you work with heavy, articulated machinery, you already know that taming high-pressure fluid is an absolute art form. So here's a real mechanical mystery for us. How exactly does a massive articulated loader steer smoothly under, say, 4,000 psi of pressure without the violent kickback literally snapping the driver's wrists? Well, we're going to break down exactly how this heavy machinery manages that kind of massive pressure safely and, of course, efficiently.
To really grasp the big picture here, we need to kick things off with understanding load sensing control.
So, load sensing. At its core, it's a pump control system used in open circuits. What it does is sense the load-induced pressure downstream of an orifice, usually your directional control valve. Then, it dynamically adjusts the pump flow to maintain a constant pressure drop. You can really think of it like a highly efficient, on-demand delivery service. It supplies exactly the flow and pressure the actuator needs at that precise moment, and absolutely nothing more. Pretty clever, right?
It gets really fascinating when you compare this to the older, standard, fixed pumps. Those older setups, they just output maximum flow constantly. That wastes a massive amount of energy, converting it straight into excess heat when the flow isn't actually needed. But load-sensing variable pumps, they only produce the demanded flow. So if your winch or steering column is just creeping along slowly, the pump actually dials itself back. This makes the whole shebang incredibly energy efficient, and crucially, it keeps your hydraulic fluid from baking itself into a useless gummy mess.
Now let's take that broad theory and apply it to Danfoss steering system mechanics, which, as you probably know, is an absolute staple in large articulated vehicles. Think for a second about the sheer physical challenges of a massive loader. When the vehicle steers right, that incredibly heavy rear section naturally just wants to keep driving straight ahead. That generates some really intense, alternating negative and positive steering forces. The Danfoss flow amplifier valve steps in here to seamlessly control these forces. It keeps the vehicle stable, minimizes side acceleration on the driver, and totally prevents jackknifing.
So, the secret sauce in achieving that buttery smooth control is this absolutely crucial 8-to-1 amplification factor. See, the steering unit provides a fixed displacement of oil per revolution of the steering wheel, but that pilot flow gets merged with the main pump flow at an exact ratio of 8-to-1 right inside the flow amplifier. To put that into perspective, the total oil output fighting those massive cylinders is literally 8 times the output of the steering wheel's control unit. That gives the operator incredible leverage without snapping their wrists. Of course, none of this mechanical magic actually works if your pressures are out of balance. So let's look at pressure setup and adjustment and see how we dial these systems in perfectly. It turns out there's a very strict 4-step sequence you absolutely have to follow when adjusting these pressures. You start with the system standby pressure, move on to the pump compensator, then hit the main control valve relief, and finally do the individual circuit reliefs. Oh, and you always verify or adjust these pressures at engine idle. Actually, scratch that. You must do it at idle. If you jump straight into adjusting a circuit relief without verifying the main standby pressure first, your entire calibration will be miles off, and you're going to be chasing ghost problems all day long. To actually pull this off, you tap into specific test ports. These are typically located right at the hydraulic high-pressure filter assemblies for the implement and steering pumps. And you are definitely going to need reliable 1,000 psi and 5,000 psi gauges installed directly at these ports so you can monitor your adjustments in real time. When we're balancing these systems out, the final baseline target numbers are incredibly precise. Notice how the pump standby pressure sits way down at 600 psi, while the implement main relief gets pushed all the way up to 3,300 psi. And the steering flow amplifier relief, that sits at a very specific 2,550 psi. Honestly, getting these exact numbers locked in is exactly what separates a beautifully smooth machine from a highly dangerous, jerky one.
All right, let's shift gears from a pristine, perfect setup to the harsh realities out in the field with common steering valve problems.
Especially for low-profile vehicles grinding away in mines or on dusty construction sites, they face just brutal environments. We're looking at 5 main culprits here: contamination, leakage, cavitation, pressure fluctuations, and temperature extremes. These will rapidly degrade your steering performance. Take cavitation, for instance. That happens when vapor bubbles violently collapse inside the system, sending literal shockwaves. Shockwaves that can pit and completely erode the valve's internal metal surfaces. It's wild stuff.
But out of all those issues, the primary suspect? It's almost always dirt. The absolute crucial takeaway here is that dirty fluid is the #1 enemy of your hydraulic system's delicate internal orifices. It's kind of crazy to think about, but even microscopic dust can completely clog the valve's passages. That leads to erratic behavior, jerky steering, and premature wear on the spool and sleeve. Okay, so let's get into fixing these problems safely and logically with systematic hydraulic troubleshooting. Now, before you grab a single wrench, I cannot stress this enough. These systems operate between 2,000 and 5,000 psi. High-pressure fluid injection is lethal. It will penetrate your skin instantly. It's a fascinating but incredibly dangerous reality of the job. You must always, always completely relieve system pressure and lock out the power before touching these valves. And absolutely never use your bare hands to feel around for an invisible leak. Once you've made sure everything is safe, we arrive at the classic question. When you're standing in front of a dead or drifting system, this is the first thing every mechanic asks. Is the valve bad, or is it something else? Surprisingly, before you go tearing into the messy mechanicals, you should always check the electrical side first. Grab your multimeter. Check both the voltage and the resistance at the solenoid terminals, which are usually 24-volt DC or 110-volt AC. The reality? Most so-called valve failures are actually just failed electrical coils or a safety interlock that's preventing the valve from firing. Now, if the electrical side does check out, you're going to want to follow a systematic 7-step process. By walking through these steps, like using the manual override to separate the mechanical from the electrical, checking the overall system pressure before just blaming the directional valve, and inspecting for internal contamination, you completely eliminate the guesswork. You isolate exactly where that pressure drop or blockage is occurring instead of just throwing expensive parts at a ghost problem. For those really stubborn issues that don't present an obvious leak or electrical fault, you can run 3 advanced diagnostic tests. The cylinder drift test, that's going to reveal internal leakage in the directional control valve. A pressure decay test monitored over 15 minutes will highlight any unacceptable pressure drops. And temperature monitoring is just absolutely vital. Fluid bypassing a worn seal creates serious friction and excessive heat, which then literally cooks the rest of the seals in the entire system. Which brings us to our final and definitely most important question. Let's say you found a stuck, overheated valve and you replace it. Are you actually fixing the problem or just treating a symptom? Because if your hydraulic cooler is plugged with debris, roasting your oil and turning it into gummy varnish, swapping in a shiny new valve isn't going to save you. It'll just fail again next week. You have to track down the true root cause, whether it's a clogged filter, a bad pump, or a failed cooler. Fix the system, not the symptom. Honestly, it makes you wonder how many millions of dollars are wasted every single year replacing perfectly good valves just because a microscopic piece of dirt wasn't tracked back to its source.